Hello, this is John Wallace, Senior Editor at Laser Focus World, and welcome to today's webcast brought to you by Laser Focus World Online. Today's event, Accuracy of Combined Scanning and Servo Systems, will be presented by Ron Rekowski, Director of Product Management at Aerotech. Following the talk, we'll have a short question and answer session. You can ask questions at any time during the presentation via the web using your Ask a Question box by clicking in the open area and clicking the Ask Question button to submit. If you should need technical assistance, please type your inquiry into the tech support box on the left side of your screen and click the Send button. It's recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the homepage at www.laserfocusworld.com. Now it gives me great pleasure to introduce today's speaker, Ron Rekowski.
Thank you, John. I would also like to thank everyone for attending today's presentation. My name is Ron Rekowski, and I'm responsible for product management at Aerotech. Today I'm going to discuss how to get the best possible results from systems that use both scanners and servo stages in micromachining and marking applications. Following is a summary of what I'll be discussing in today's presentation. For the sake of completeness, I've included a slide that shows a common configuration of a combined marking and servo platform, and a couple more slides that show why these type of systems are useful and the problems that need to be overcome. Then I'll begin a review of the issues that detract from final part quality. We could spend the entire presentation drilling down on just scanner-related errors such as laser alignment, mirror alignment, focus optic distortion, thermal drift, and zero offset drift. These errors, however, are not unique to this process and are present in static marking applications as well. Since the focus of my presentation is on the combination of scanners and servo axes, I will pretty much treat the scanner as a black box. There are some first-order error measurements we can use to categorize scanner performance and combine these values with our system-level calculations. At the close of the presentation, I will discuss a different approach to improving applications that must create long, continuous patterns whose size exceeds the field of view of the scanner. The image on the right shows the most common configuration for a combined scanner and servo system. The scanner is mounted to a Z-axis to allow for focal adjustment, while the material to be processed is attached to a moving XY axis. This system, however, is not the only possible configuration. If the material is too large to move or is part of a reel-to-reel process, the scanner can be mounted on an overhead gantry. There are two sets of XY coordinate frames in this system. One frame, shown by the red arrows, is created by the scanner, and the other, denoted by the blue arrows, is for the plane created by the servo axes. To achieve the best possible marking quality, we want to get these two coordinate frames aligned as closely as possible. So now that we know what these systems typically look like, the next question is, why do I need to use them? The image on this slide shows a pattern comprised of many small features scattered over a large area. The area to be processed is much larger than the field of view of the scanner and is indicated by the blue outlined box. The traditional approach to marking this object is to expose the part of the material under the scanner, move the material to the next area, and then repeat. An alternative solution would be to use a longer focal length optic that provides a work area equal to the size of the part. However, there are practical limitations that limit this approach. As the working area of the lens increases, the spot size of the laser increases proportionally. Also, the optics magnify the positioning errors of the scanner. A larger field of view will have lower feature placement accuracy when compared to a smaller field of view. Typically, users start with the desired spot size and laser technology, then use this information to determine the focal length of the optics and the size of the field of view of the scanner. Okay, seems simple so far. You attach your part to a set of XY stages and then move, expose, and repeat until the entire part is processed. The problem with this approach is that the final marking quality is limited by the combined accuracy of the scanner and servo stages. Lines which cross the boundary between two move and expose events are not continuous. Also, when you do manage to line up the marks, there are issues with ensuring an even distribution of laser power between the end of one mark and the start of another. The images on this slide demonstrate this effect. The illustration gives a quick visual effect while the photos show some actual alignment results. The remainder of this presentation will discuss the sources of these errors and how to minimize them. Lens calibration is one of the sources that I referred to earlier that we could spend an entire presentation on. Scanner systems use special optics to flatten the focus plane of the scanner. The configuration of the mirrors in the scanner also result in pincushion and barrel effects on the marking plane. The focusing optics attempts to correct for these errors while also providing a flat focus plane. The lens is not perfect, and there are other variables such as the distance between the mirrors and the scanner and the alignment of the laser to the mirrors that detract from final marking quality. Lens manufacturers will supply a theoretical 2D calibration file based on the configuration of the scanner and their optics. However, for high accuracy application, these calibration files need to be optimized on the system. This typically involves marking a grid pattern and measuring the accuracy of the pattern. The 2D calibration file is then modified to improve the performance. One iteration of this process is seldom sufficient. The mark and measure procedure is repeated until the desired results are obtained. In the end, the accuracy of the scanner itself, usually given in rotational displacements of the mirrors, will limit the achievable accuracy on the part. The 2D accuracy resulting from this test is a critical limiting factor in the final combined scanner and servo system accuracy. Users of scanners are aware of the impact of the scanning height on scaling and part size on the surfaces of the part. If you are too close, the image shrinks. Move too far, and it stretches. In addition to changing feature sizes, the spot size and the resulting line width will also change. Setting the focal position is a static setup operation and typically stays unchanged during a 2D processing application. However, when the stage is moved, the Z height of the material can shift. Flatness is a common performance specification for a linear positioning stage, and its impact on system accuracy can be easily assessed. Angular errors, such as pitch and roll, also contribute to focal errors. The Z height deviation can be calculated based on the stage displacement and the angular error. Keep in mind that the pitch and roll specification for a linear stage are typically given for a fully supported stage. You'll need to ask your stage supplier for information regarding anticipated pitch and roll values for an XY system with a given load. The scanner and servo axes are two separate 2-degree of freedom Cartesian systems. The coordinate frames of both systems need to be aligned as closely as possible. Stage systems consist of bolted XY axes, and the alignment of these axes is held to a tolerance, typically on the order of 5 to 10 arc seconds. The image on this slide shows a non-orthogonal alignment of the XY axes used to make the red square. Modern control systems will have correction routines that can be used to correct for this error and provide effective alignments in the single arc second range. If you have calibrated your lens with the grid pattern measurement technique described earlier, then the orthogonality of the scanner system has already been addressed. Once the scanner and servo axes are making squares of sufficiently good quality, the orientation of their coordinate systems needs to be aligned. Most scanner systems have the ability to rotate the field of view. Once the angular offset between the scanner and the servo axes are measured, this angle can be used to rotate the plane of the scanner into alignment with the servo stages. Straightness and to a greater degree yaw are also stage performance specifications that can impact final part quality. Straightness is a fairly easy error concept to understand. As the stage moves up or down, as shown in the illustration, the actual motion can deviate to the left or to the right from center. The impact of yaw, however, is less straightforward. It can be viewed as a change in rotational alignment between the XY coordinate frame of the scanner and servo axes. The impact of this error changes depending on how far away the marking operation is from the center of the rotation point and the amount of rotation at a given location. As you can see in the illustration, the X and Y error components for marking operation on the edge of the field of view changes depending on the degree of the rotation and the distance from the point of rotation. Pitch and roll also impact marking accuracy. These angular errors shift the height of the material, as I mentioned earlier in the focusing discussion, and they also affect linear part placement on the accuracy. So there are a number of error sources that we have detailed on the previous slides that all contributed to final system marking accuracy. For a first-order combination of these errors, we can calculate the 2D error contribution of the XY axes and the yaw and add these up in a root sum squares estimation. Once this is completed, we can add the 2D error of the scanner as determined from our grid measurement test. I'll do an example calculation of this over the next couple slides. Let's assume we are working with a 300 by 300 millimeter travel stage with catalog performance specifications listed here. We'll ignore roll, pitch, and flatness errors for this example. Typically, their contribution is small compared to the other values we will take into consideration. For the calculations, we are assuming the same performance specifications for the X and the Y axes, and we will combine these errors as vectors. The bottom axis calculation is based on the sum of squares of the single axis accuracy, straightness, and yaw over the travel expressed in microns. The top axis has the same terms, but an additional contribution from orthogonality errors. We end up with an x-axis error around 26 microns and a y-axis error of around 30 microns. Combining these two errors into a final 2D vector error, we end up with around 40 microns of 2D error over 300 by 300 of travel. An achievable 2D accuracy for a standard scanner is on the order of 20 to 30 microns over a field of view of roughly 50 by 50. If we combine this error with the calculation from the previous page, we end up with approximately 60 microns of 2D error. If the process has low tolerance and a spot size much larger than 60 microns, then this may not be an issue. But if you're working in a high-precision micromachining applications and have spot sizes smaller than 60 microns, or need to hold uniform spacing on the order of tens of microns, this error will have a significant impact on system performance. How to improve performance? First off, make sure you're using components that are up to the task. Higher quality linear stages will have smaller error signatures. Also consider performing a 2D calibration of the stages. This process consists of attaching a plane mirror to the XY stages and measuring positioning accuracy in two directions simultaneously. This technique also measures orthogonality and straightness errors. It will ensure that the center of the field of view of the scanner is in the correct location even in the presence of yaw motion. It cannot, however, remove the off-axis yaw errors that occur when the marking takes place off the center of the field of view. The graph on the right shows an XY system before and after 2D calibration. Before calibration, the 2D accuracy was in the order of 50 microns. Afterwards, single-digit 2D accuracy is attained. There's also a graph that shows orthogonality and straightness errors before and after calibration. You can clearly see the impact of 2D calibration on these error sources. Another technique that I won't go into, again, we could probably do a complete presentation on that, is to use vision to detect where objects end between successive marking sequences and make adjustments. This process is a bit more involved and results in increased cycle times as the camera needs to acquire, process the image, determine the position of the objects, and communicate this information back to the motion program. In addition to higher quality servo stages and applying 2D calibration, consider using a higher accuracy scanner. Modern scanner technology uses much improved encoder and motor technology that improves static and thermal accuracy. Attached is a plot from a high accuracy scanner shown over a 40 by 40 millimeter field of view in which single-digit micron level 2D accuracy is obtained. If you're getting 20 or even 10 microns of 2D accuracy from a scanner, moving to a higher accuracy device can reduce this error by a factor of 5 to 10. A quick test to determine the quality of the combined system accuracy is rather simple. Start by marking a pattern to the edge of the field of view of the scanner with both the scanner and the servo axes and measure the offset between these marks. We typically use two different references so that the source of the mark can be easily identified. In the image I show a plus sign is marked by the stage and an X by the scanner. By observing the relationship of these marks, it is possible to determine the error sources and the process to correct them. In this illustration, the X marks from the scanner are all running short, that is, they're all inside the marks from the stage. This would indicate that the scaling or the focal position of the scanner is incorrect. The pattern is also rotated relative to the servo stages. To correct for this error, the field of view of the scanner will be rotated into alignment. After optimizing the alignment of these marks, the remaining error is a best case 2D accuracy, as actual marking quality will be worse over the full travel of the servo stages since this test does not factor in yaw-based errors. The test could be repeated, however, at multiple locations over the work area to assess the full impact. All the issues I've outlined deal specifically with physically aligning marks that end at one edge of the field of view and continue on another. The analysis also gives an idea of the final placement accuracy of features over the entire working area. This analysis does not, however, address process issues that arise when features cross marking boundaries. The laser spot displacement and power density can be impacted at these locations as the laser transitions from turning off at the edge of one field to on again at the edge of an adjacent field. One solution to this problem is to not stop between the fields, but instead move the stages in a continuous fashion. Aerotech has a process through which the motion commands for a part whose size exceeds the field of view of the scanner are split between the servo and the scanner motions. With this approach, the axes move in a continuous fashion while the scanner continues to mark. The video on this slide demonstrates the marking of a continuous feature that exceeds the size of the field of view of the scanner. tracking the moving material. The motion of the material is not controlled within the same program or even the same controller as the scanner. Here is another example where the scanner is marking many small features spread over a large area. Each of these features fits completely within the working area of the scanner, with the part being significantly larger than the field of view itself. This system also represents an alternative system configuration where the material is stationary and the scanner is moving. This approach is preferable when the part can't be moved due to size, stiffness, or mass issues of the material, or if the material is part of a reel-to-reel process. And I believe there was supposed to be a playing of the video here, but I don't see that, so we're just going to continue on to the next slide. So, okay, to summarize, the biggest takeaway from this presentation is that final marking quality is no better than the weakest link in the system. Make sure you test the combined performance of both systems by marking test patterns and making adjustments as required. This may seem obvious, but we have run into situations where users have bolted together components, then wondered why the resulting part quality was very poor. For the best possible accuracy, consider 2D calibration of the servo stages, as this addresses many of the error sources introduced by these components. When accuracy requirements demand it, make sure you're using a modern, high-accuracy scanner capable of obtaining single-digit 2D accuracies. And finally, if possible, consider marking in a continuous fashion to ensure consistent feature quality across the entire part. I thank you for your time and look forward to your questions.
Well, good afternoon. We've reached the Q&A portion of the webcast. So to ask a question via the web, type your question into the open area of the Ask a Question box and click the Ask Question button to submit. So that was pretty impressive, demonstrating the marking on moving material. How does the movement of the material impact marking accuracy, though?
This is a good question, and one that we get asked all the time, basically. The movement of the material causes the scanner to move and to accelerate faster than it would otherwise if it were marking a stationary object. However, it's quite possible to estimate this impact on part quality. For a modern control servo loop, which obviously we're using in this case with acceleration and velocity feed forward, the peak position error occurs during peak acceleration, and basically they are proportional. You double the acceleration, you double the position error. So if you were marking a stationary part and you had a peak acceleration of 10 Gs and you saw a peak error on your part of 2 microns, you can use that relationship to roughly estimate the error contribution when the material is moving. So worst case is that the acceleration of the material adds to the acceleration of the part, which gives you a higher peak acceleration. So if your material is moving at a peak acceleration of, say, 1 G, then your peak acceleration combined between the two is going to change from 10 G to 11 G. So this is, say, a 10% increase in acceleration. So you would expect to see a 10% increase in position error. So going back to that, what we said, we saw static 10 G and 2 micron. So at 11 G, you would expect to see approximately 2.2 microns. Not necessarily a significant error. The speed of the material, however, in addition to the acceleration, can also impact the marking accuracy. But it mostly contributes to arcs and circles. When you have an arc or a circle, there's an acceleration that is proportional to the velocity squared divided by the radius of the acceleration. So the acceleration in that arc or circle goes up by the square of the increase in velocity. If you know the smallest radius you have in your process, you can add the speed of the servo axes to your processing speed and see what kind of acceleration increase this results in. Again, so if you end up doubling the acceleration, you'll end up doubling your peak error. So again, there are some quick ways to just do some basic math to figure that out.
Okay, and why? What would be the reasons for using this method, the marking on moving material, versus just marking on the fly?
Again, as I mentioned that on the previous slide, marking on the fly the material typically just moves in one dimension. So it was developed mainly for reel-to-reel applications. And historically, the items you were marking fit entirely within the field of view of the scanner. So you were going to just mark them as they came by. And it was really sort of like a gearing application. So you looked at the moving material as a master, you fed that into the scanner, and when a part, when an object to be marked comes within the field of view, you added the motion of the material to your marking of one axis, and then you mark that part. This is different because it works in two axes. So the material can move in X and it can move in Y. And also now the movement of that material, rather being dependent, whereas you had this reel-to-reel process where it's moving at some speed that's defined upstream by some process, the speed of your material is now based entirely on your marking process, on the features that you want to mark. So the distance that it moves, the speed that it moves, is all based on the features that you're placing on the part.
Okay. Can you describe Aerotech's scan field calibration method?
Yeah, our calibration method is basically we have a small setup in our lab where we have a fiber-delivered YAG laser. We have some glass substrates with a metallic thin film on top of it, and we mark some fiducials over a pattern. So in that example, our field of view was 40 by 40 millimeters, and I think that might have addressed another question that popped up. So I think we marked at a placement of, say, every 2 millimeters, a 2 millimeter grid over that 40 by 40. And then we placed that on a high precision XY state setup, 2D calibrated with laser interferometer feedback, and then a high resolution Cognex camera system. And then we move and record the positions of these fiducials that we've marked over that 2D grid. And then from there we generate an error map.
Okay. How do changes in temperature affect part quality, or do they?
And they do, and temperature changes are a big problem in any motion system. Basic laws of physics, materials expand when you heat them, and this expansion causes a degradation in accuracy. When accuracy really counts, customers who use servo systems put them in controlled environments where they limit ambient temperature variations. Also, your stages need to be sized to ensure that the motors are not generating excessive heat. That heat migrates through the systems. Scanners have multiple thermal-related issues as well. The housing can grow, which changes the offset between the mirrors. Older scanner technology has feedback devices that have very, very well-known issues with thermal drift and offset that impact accuracy. You basically go to any scanner manufacturer, and one of the specifications you'll see is thermal drift or an offset drift versus temperature and also over time. So for the scanner, if accuracy really matters, you want to use some of the newer devices that use optical encoder-based feedback, which have better thermal stability. And then there are heat sources inside the head itself, the galvo motor. So we consider water cooling as an option to remove the heat generated by these motors. And the last one, you don't have quite the same level of flexibility on in terms of suppliers, but most scanners nowadays also have the power electronics integrated into the head. Power electronics are heat-generating devices, so they are going to put, they're going to put some watts into that laser head. And when you first power on in the morning, they're going to be stone cold, and as you start to use them, they're going to heat up, so they're going to contribute to a degradation in accuracy. So one thing you might consider for an extremely accurate application is to use remote power electronics. So the head basically just becomes two motors, mirrors, and optics. And again, you want to pay careful attention to all the thermal sources. This analysis holds true. Like we do it for servo systems. You need to do that also with your scanner system.
Mm-hmm. How much less significant are pitch and roll errors than straightness errors usually?
Obviously, it depends on the magnitude. So the pitch and the roll, the pitch to a less degree, but the roll to a greater degree when you have an XY stage. When you go unsupported, that degree of roll that occurs is a function really of the load. So it's a simple calculation, right? And it scales linearly as a function of displacement. How far you're moving out over the unsupported center of mass. I would say that for most cases, they're typically on the same order of magnitude. So your straightness error versus your calculated pitch or roll at the work point are going to be fairly similar.
How high can the resolution be for a marking scanner?
Well, that depends on the technology of the scanning system that you're using. Historically, most scanners are 16-bit resolution, and they've been that way for quite some time. There's a standard communication interface called the XY2100 that propagated to many suppliers, and that was basically a 16-bit position that was serially transmitted. And to a large part, a large percentage of the scanners adhere to that 16-bit standard. As I mentioned, there's newer scanner technology out there now that are using optical encoder devices, and these devices have basically output signals that have multiple periods over the travel of the galvo. So there are galvos out there right now that'll do 20 bits, 24 bits. I know we have a device whose final resolution is actually 26 bits over the field of view.
Oh. During the presentation, a giraffe was engraved. Was the giraffe done with lines and arcs? In other words, a vector marking?
Yes, all those operations that I showed in the video were vector operations. And this technique can be applied to bitmaps, but there's less of a payoff there. It works well to extend the bitmap in one direction, to extend it in an X and a Y. Because at the end of the day, a bitmap is usually a raster scan operation, and a raster is done at a very, very high speed. So if you have to do part of the rastering, so let's say if you exceed it in both X and Y axes, then one of those axes are going to basically handle part of the motion of the scan, if you will, on the raster. So your effective raster speed is limited by your servo speed. And because that raster runs at a very high duty cycle, it's also very demanding for the servo stages to move the mass at that same rate. So technically it's possible to do bitmaps in raster scans like that, but practically you want to limit the overrun in the image to one direction.
Mm-hmm. Does Aerotech make their own galvo motors?
We have our own galvo assembly, basically, our own servo stage system, our own scanner assembly. So yes, we do offer a complete assembly.
And we have a note from the person who asked the question about the highest resolution of a marking scanner, and he says he was meaning the length in microns, not the digital resolution.
Okay, I mean that's easy enough to calculate. So, and really the length in microns on the surface depends on the optics you're using, right? So, if you have a 40 by so basically your effective resolution, you look at your galvo motor has say 20 degrees of motion. So the resolution is typically specified over that motion. So if I say I have 26 bits of resolution, it's over 20 degrees of motion on the mirror. That motion then gets converted to linear motion by the optics. So if I have optics that have an effective 40 millimeter by 40 millimeter field of view, then you take 40 millimeters, you divide that by 2 to the 26th, that's your effective resolution. Now you could have different optics on there that give you just to go completely opposite, 300 by 300, 300 millimeter by 300 millimeter. So then again, your resolution is, will take 300 millimeters divided by 2 to the 26th, and that's your effective resolution. So the resolution really it's a system level dependency. So you've got the fixed resolution of the mirrors over their angular displacement, and then you've got an amplification that occurs through the optics.
Okay, I think that wraps up our question and answer time. Ron, I want to thank you very much for your presentation with Laser Focus World, and on behalf of Laser Focus World and Pinwell Corporation, I would like to thank today's speaker, Ron Rekowski, Director of Product Management, Aerotech, and our sponsor, Aerotech, for today's presentation of accuracy of combined scanning and servo systems. This presentation will be archived within 24 hours and can be accessed from the homepage at www.laserfocusworld.com. A reminder email message for the archive will be sent to registrants, complete with a direct link to the archive. Again, we thank you for joining us today and look forward to future webcasts.